Hey everyone, and welcome back to another explainer. Look, if you're getting ready to conquer your upcoming physics exams, you are in the exact right place. Today, we're cracking open Chapter 2 of Thermal Physics. I'm honestly thrilled to guide you through this material because we're going to break down some of the absolute trickiest concepts into simple visual frameworks that will actually stick in your memory. We're talking molecular kinetic energy, internal energy, and the fundamental mechanics of heat transfer. So get ready to lock in those high marks. But before we really get going, I want you to think about this classic exam trap. Which object actually possesses a higher total energy? A steaming hot cup of chocolate or an entire massive frozen lake? I mean, it seems like an obvious answer, right? Hot chocolate is hot, ice is cold, but this exact scenario tricks thousands of students every single year because it plays on a really common confusion between temperature and total energy. So keep your answer in mind because we're going to solve this together very soon. Okay, here's our roadmap for today. We'll start with temperature versus internal energy. Second, thermal equilibrium traps. Then, we'll cover conduction, convection, and radiation. And finally, exam mastery. All right, Section 1, temperature versus internal energy, and really understanding the difference. Okay, let's dive right into this, because mixing these two up is literally the #1 reason students lose easy points. The textbook definitions are incredibly precise, and you need to know exactly what the examiners are looking for. Temperature is strictly a measure of the average kinetic energy due to the random motion of molecules in a body. Remember, it's just an average. Internal energy, on the other hand, is the total amount of molecular energy stored in the body. That includes the total kinetic energy of all the molecules added up, plus the total potential energy that comes from the attractive forces holding those molecules together. To make sure you never forget this, I want you to visualize a dance floor. Just picture temperature simply as the average dancing speed of the people out there. If the music's fast, the average dancing speed goes up, so the temperature goes up. But internal energy? That's measuring the total energy of the entire club. It accounts for how fast they're dancing, plus how many dancers are actually in the room, plus the energy keeping them grouped together. Moving right along to Section 2, thermal equilibrium, and how to crack those sneaky exam traps. Whenever you see a question where two objects touch, I want you to run this exact 3-step logical framework. Step 1. Heat flows from the high-temperature body to the low-temperature body. And notice, I said heat, which is the transfer of energy. Exams will totally try to trick you by saying coldness transfers. No way. Coldness is not a physical thing. Only heat energy moves. Step 2. This energy transfer stops the exact moment they reach the same temperature. That's what we call thermal equilibrium. Step 3. Remember the law of conservation of energy. The total energy lost by the hotter body perfectly equals the total energy gained by the colder body, assuming none of it escapes to the room. So, let's bring back our hook question. The cup of hot chocolate versus the frozen lake. What's the answer? Well, the frozen lake actually has a massively higher total internal energy. Yes, the hot chocolate has a higher temperature, meaning its individual molecules are dancing faster on average. But the frozen lake has trillions and trillions more molecules. When you add up the total energy of all those individual water molecules in the lake, it totally dwarfs the total energy in that tiny little cup. So, whatever you do, don't let a high temperature blind you to a low mass on test day. That brings us to Section 3, conduction, or as I like to call it, the domino effect. We know heat transfers from hot to cold, but exactly how does it do that? If you're asked to define conduction, you want to use this exact wording. Conduction is the transfer of heat from the hot part to the cold part of an object, or between objects and physical contact, without transferring matter. That last phrase is absolutely key. The energy moves, but the physical material itself stays exactly where it is. Our visual mnemonic for conduction is a domino effect, or maybe a relay race. Imagine atoms locked tightly in a solid structure. When you heat one end, those atoms gain kinetic energy and start vibrating rapidly. They literally physically bump into their slower-moving neighbors, passing the energy to them. Those neighbors then bump the next ones, and so on. The energy just races down the line, atom by atom. Now, exams love to ask why metals are overwhelmingly the best conductors. It's because they have a secret weapon. While regular solids only have those vibrating, tightly packed atoms bumping into each other, metals also have an abundance of free electrons zooming around inside them. These free electrons act like VIP runners in our molecular relay race. They don't just bump their immediate neighbor. They grab the thermal energy and sprint down the metal, colliding with atoms much further away. That is exactly why a metal spoon heats up instantly when you drop it in your hot soup. Okay, Section 4, convection. Think of this one as the fluid elevator. Now, what's really interesting about this is when we shift our focus from solid objects to fluids, meaning both liquids and gases, we get a whole new heat transfer method. Unlike conduction, where the atoms stay mostly put and just pass energy down a line, convection is the process of heat transfer in a fluid by the actual movement of the fluid itself. Matter is physically moving from point A to point B, carrying the heat right along with it. The easiest way to picture this is the fluid elevator mnemonic. Think about boiling a pot of water. The heat source at the bottom warms the water directly about it. That hot water expands, which makes its density drop. Because it's lower density, it rides the elevator straight up to the top. Meanwhile, the colder, denser water at the top is heavier, so it sinks down to the bottom to replace the hot water. This creates a continuous cycle called a convection current. Hot fluid rides up, cold fluid rides down. Next up, Section 5, radiation or invisible heat waves. So we've covered solids and we've covered fluids, but what about when there is absolutely nothing? Radiation completely breaks the rules we've established so far. It is a process of heat transfer which absolutely does not require any physical medium or particles to work. It takes place in all directions, traveling through pure empty space. This is precisely how the Earth gets energy from the sun across millions of miles of the vacuum of space. And this brilliantly illustrates what examiners will frequently test you on: the properties of an object's surface regarding radiation. A dull black surface is an incredibly good absorber of radiation, but it is also a fantastic radiator, meaning it emits energy very quickly. On the flip side, shiny, silvery surfaces are terrible absorbers because they reflect radiation, and they're also terrible at emitting it. You also need to know that a larger surface area and a larger temperature difference between the object and the room will both increase the rate of radiation. Lock in this final mnemonic. Visualize radiation as invisible waves. Specifically, at room temperature, objects are emitting invisible infrared waves. Literally everything that is above absolute zero is constantly emitting and absorbing these invisible waves. Even you, watching this explainer right now, are radiating infrared energy out into your room. Crazy, right? Finally, Section 6, Exam Mastery. This is where we combine all these concepts. Real-world engineering rarely deals with just one transfer method. So the crucial point here is knowing how to analyze something like a vacuum flask, a thermos. This is a guaranteed must-know exam favorite because it tests everything at once. Why does it keep drinks hot? First, the vacuum between the double glass walls literally removes the physical matter, making conduction and convection completely impossible across that gap. Second, the walls have a shiny silvery coating, which acts as a mirror to reflect infrared radiation back into the hot drink. And finally, the plastic lid at the top prevents hot air from rising and escaping, shutting down those convection currents. One single device defeating all three heat transfer methods. Well, we've covered a huge amount of ground today, from the microscopic difference between temperature and internal energy, to the dominoes of conduction, the elevators of convection, and the invisible waves of radiation. I want to leave you with a challenge to really cement this knowledge. Look around the room you're sitting in right now. What is one item, right near you, that was specifically engineered by humans to either prevent or encourage heat transfer? Spot it, identify the physics at play, and I promise you, you'll be more than ready for your exam. Thanks for joining me on this explainer, and keep learning.